Welcome learners. Today's lecture is about operational amplifiers. We are going to see the importance of this electronic device, which is the foundation for basic building blocks of various electronic components that we see in our surroundings today. Let us see what the op amp or operational amplifier is all about. So, operational amplifier was first created by a Fairchild Semiconductor company in the year 1968, and this technology came into existence because after the Second World War the researchers wanted to miniaturize the elements that we had. The main idea was at that time the processing was done with the help of analog computers. So what were the possible options available such that they can reduce the size of these devices, and operational amplifier was one of the electronic component that paved the ways for miniaturization of devices along with transistor, semiconductor diodes. So once this device was created, its applications were enormous, and till date it is being utilized sufficiently. Let us look into the further details of this operational amplifier, or as the engineers commonly call it, as an op amp. On to your right you can see the practical op amp in its full form. We are going to look into the construction of this op amp, what are the legs or pins of this operational amplifier, what are the symbols or the writings on the top of the black jacket, what is this circle over here, what is the meaning of this notch over here. So all these things will be discussed in today's discussion. So as I mentioned, operational amplifier or op amp is an electronic device. Now the question appears that our course is about linear circuit analysis, or we are talking about electric circuits. So how can we discuss an electronic device if we haven't studied the course of, or the basic course of, electronic devices and circuits, or normally electronics 1. So let us first understand the main differentiating factor between an electric circuit and an electronic circuit. What is the thing that differentiates between the two? After that, we can see, or we are going to see, that since it is an electronic device, our op amp is so versatile that it has become a basic circuit building block, which means this device can easily be integrated with the basic RLC components. Those RLC components are a resistor. We will later see about the storage elements like capacitor and inductor, and obviously the remaining two are always there to energize the circuit, and those two are the voltage sources and the current sources. So the versatility of this device is going to be discussed with examples in this lecture today. So let us come back to the comparison between an electric circuit and electronic circuit. So always remember that electric circuit is a guided response. On the other hand, an electronic circuit is guided, but we add the element of control to it. So it is a controlled response with the guided response. What does it mean? So let us look at an example, a very basic example. Let us say I have a DC voltage source, certain resistor, and it is connected to a load. So this is the voltage source, this is any resistor, and we have a load. And let us say that the load in this case is an electrical bulb. So this is the electrical bulb. So whenever we switch on the button, the current starts to flow. Voltage source being our AC source, it is converted into a DC source with the rectifier, and the current starts to move and the bulb will start to glow. So this is basically the guided response of any given electric circuit. The guided response is such that we have defined the paths from voltage towards the resistor, then resistors to the load, and then the circuit gets completed when the current comes back to the negative side of the terminal. Now what happens in the electronic circuit? So you can see it's a combination of guided, but the control element is there. So the guided response remains the same, that we have defined a certain path shown here by the red overlay, but the controlled element is such that now once the switch is pressed to be on, the bulb starts to glow. So this is the electrical part. Control part enters, that let us say you might have seen that we want to control the brightness of the bulb, how much bright or how much light we want to control illuminating from the bulb. So this control aspect brings us to the domain of electronics, because now this control literally means, so controlling means we are controlling the flow of charges, and hence nowadays most of the devices are referred to as an electronic device but not an electrical device, because most of the components in our gadgets, for example smartphones, tablets, laptops, any device which we are using as an electrical device or electronic device, is basically we are using those components to control the flow of charges. So this is the important difference between an electrical circuit and an electronic circuit. That's why we say that op amp is an electronic device, because inside the elements or the flow of charges are controlled, and as such the device itself as a whole is used to perform different operations. So now this is the difference. Hope it is clear. Now let us come back to the characteristics of the op amp. So we know that it is an electronic device. Engineers normally call this as an op amp, and this is in the form of an IC. An IC is basically an abbreviation for integrated circuit. So this is known as an IC. So basically it has multiple components inside, and we bring it to a size of the millimeters probably in to basically make it as compact as possible. So this all package over here is known as an integrated circuit, because it can be installed into different components inside the circuit, and within this circuit there is multitudes of transistors. So inside this op amp, we are going to shortly see, is multiple sets of transistors performing or working together to make the operations of this op amp complete. So now let us come to the name op amp and see why it is called an operational amplifier. So we should remember that operational or op amp is the combination of two words. So it is operational plus amplifier. What does it mean? So operational amplifier, so first let us understand what is the purpose of an amplifier. So generically speaking, amplifier is nothing but a device that increases the performance of any system in terms of its strength, power or voltage. So let us say if I have any input signal represented by a sinusoid. So horizontal axis is the time domain, and this is the amplitude or the strength of the signal, and this is my input signal. Whenever this input signal passes through, let us say, an amplifier, the amplifier is going to perform an action on this by giving us the output. So let us say the input signal was at 5 volts. Now the output will be amplified to 10 volts. So you can see ideally an amplifier is basically going to increase the strength or the amplitude or the voltage of the signal. Hence we say that the signal gets amplified. The simplest example or the daily life example will that be of a megaphone. So if you speak into a megaphone, your voice is at a lower decibels, but the output that is coming out from the megaphone gets amplified. So the voice is heard in the farthest regions. So this is the example of an amplifier. Now what about the operational aspect of it? So the main thing that differentiates a simple amplifier or a transistor, so this is basically, again we are going into the electronics domain, but just to give you an idea. So if I have any generic transistor, let's say an NPN transistor, this is the base, collector and emitter of it. So how we are going to differentiate an op amp to a simple transistor? It can be a BJT or a MOSFET. So let us stick to bipolar junction transistor. So the difference between a simple transistor and an op amp is a simple transistor is basically going to amplify the signal, which we have seen over here. But an op amp can do both things. The first thing is that it can amplify the signal and it can perform various operations. What are those operations? These are the mathematical operations that it can perform on the amplified signal as well. So basically, when the first op amp was created, it was created to be used with analog computers of that time or era, and the idea was how can we increase the computational power of this analog computer, and hence the mathematical operations can be performed by the op amp. And the notable operations are that it can do integration, it can do differentiation, it can do scaling, which means we can increase this by a factor of alpha. It can also do addition, subtraction, or we normally say it can change the sign of the signal. So these are the basic operations that an amplified or op amp can do along with the amplification, and hence this device makes it more versatile compared to a simple basic amplifier. So now you know what is the operational amplifier stands for and how we are going to utilize this. Now let us look at an op amp and see what are the elements that makes up the amplifier. So again, this is the IC over here. We call these as the legs or the pins of an IC or the op amp. Here you can see the front view, or normally we say the top view of the op amp, and there are certain markings on this. For example, this is the IC which is named as LM741. What does this LM741 stands for? We are going to look into that shortly. Again, the pins descriptions have been given over here. We are going to look into this. All these things are basically provided in its data sheet. So whenever you purchase any electronic component, you get a data sheet from the vendor. Vendor is the person who is making this device, and basically they tell us that at how much voltage it is going to operate, what is the maximum output voltage, which pins performs which actions. So this is what we are going to see shortly. Now let us look what is inside of this IC. So as I mentioned, it is an integrated circuit. Obviously it can be placed into any component, but inside this small IC, inside this black jacket, this is what is happening. So this is the internal circuit diagram of a normal LM741 non-inverting IC or non-inverting configuration, and you can see it's a jumble, or it's a maze of different electronic components, and the main component is a transistor represented by a symbol. So you can see it's a combination of various transistors, voltage sources, the RLC components that is making this whole IC function. So again, luckily for us or for you guys, that in this course we are not going to study what is happening inside the IC or the op amp. We are just going to stick to the terminal behavior. So our main goal for this course and this chapter is to study the terminal behavior of the IC or terminal behavior of op amp, which means that we are only going to study how the voltages and currents behave between these pins or at the input and output pins, and we are not interested at the internal working of this internal circuitry of op amp. So for this course we are not going to study the internal circuitry, which means all the elements or configurations that you see here. We are only going to talk about the terminal behavior of the IC. By terminal we mean what is the voltage and current appearing across these pins. But the internal circuitry is a very important aspect which you are going to study in the electronics or basic electronics course. But let us have a look of this circuitry over here represented in the blue configuration. So again, it's a basic multitude or multiple use of transistors. Here you can see there are different combinations that are utilized. So normally we call this as the mirror configuration. Some of the part is called the Darlington amplification, where the emitter of one is connected to the collector of the other circuit. Again, base emitter collectors are the terminals of a basic BJT transistor. but again we are not going to study the internal circuitry at this stage. We are just going to stick to the terminal behavior of the circuit. The image over here was just to give you an idea how the elements are interlinked inside the op-amp. So before we proceed, let us look at a practical example of this operational amplifier, and especially where it is being utilized in the power systems domain. So one example to understand the importance of this amplifier is in the power systems domain. So normally what happens is that in any power system domains, we basically have the transmission towers from one end to the other end, and we are normally interested to keep the transmission lines as much straight as possible, ideally. But normally, due to passage of time and the natural circumstances, which means that due to hailstorm or heavy winds or rains, or other electrical losses, we normally get a bend or a curve in these wires. So the wire may become, after a certain time, bended. So the researchers or engineers are interested to see that how much bend has appeared over here. So how much bend is in the wires or in the high transmission wires. Obviously we cannot go and check each wire, so basically we take a snippet of the wire, so shown over here, one portion of the wire, we take the one section of this black wire, a high transmission wire, and we want to see that what is going to be the bending effect on the resistance of the wire. So obviously if the resistance is more, the flow of current becomes difficult, so we want to keep it as much or at a lower resistance as possible. So in order to measure the resistance of this wire, we use an element which is known as a strain gauge. So a strain gauge is something like of this form. So it is like a rectangular piece where inside you have, so these are the input points, and then you have multiple copper wires in this meander form, and then the signal goes out from here. So this is the input and output terminals, and these are the conducting wires, and all this is placed on top of any flexible material. It can be a PCB as well. So here is the strain gauge shown. So what normally happens is, whenever the wire gets bent, we want to see what is the change in resistance for the wire. So the change in resistance is given or calculated by this formula, where 2 is the scaling factor provided by the vendor. So this is the scaling factor. R is the resistance at initial stage where there is no bend in the wire. So this can be as our reference point. And delta L by L is the change or the bend in the strain gauge. So what is going to happen with the strain gauge is that if it gets bent, the wires get elongated in one direction. If it gets compressed, they return back to their original position. So we can find what is the change of resistance by bending or compression of the wires. Let us see a more practical image of this strain gauge. So this is how the strain gauge normally looks. So as I mentioned, these are the input output terminals of this strain gauge. These are the copper wires or conducting materials which measures the resistance, and this is the PCB substrate. Normally it can be a hard ceramic board or it can be a flexible PET material, and it is normally pasted onto the device. So this is a practical strain gauge, and we want to see that what is happening to the stretch. So if we basically add tension to it, the resistance increases on this axis, and if we compress it back, the resistance gets decreased. So this is how we utilize the strain gauge, and we put it on top of any wire to see the bending effect. Now let us put this all into an electric circuit form and see what we can do with the help of an amplifier. So what we have done is we have represented the strain gauge's tension and compression with the help of a bridge configuration or a diamond configuration. So we can see that R plus delta R represents the tension. So tension meaning that it has been stretched, and R negative delta R shows that it has returned back or compressed back to its original position. So this is a circuit that we can solve. We know about this configuration. We talked about this, or we know about this, that this generates from a Wheatstone bridge configuration, and this is a diamond form. So where we can simplify this complete circuit because it is nothing but an equivalent resistance where these two resistors are in series and then both of them are parallel to each other. So we can solve this to get a single value of R equivalent at this point. Once we have this value, we can pass it through the op amp. So this is the electrical symbol of an operational amplifier. We are going to look into this symbol and understand what are the terminologies over here, like VCC, negative VCC, what is this plus, what is this minus. So let us assume that we get a value from the strain gauge where R equivalent is, let's say, 0.5 ohm. So now the question appears that if we are getting the resistance from the strain gauge, why do we need to add an operational amplifier next to it? We know the purpose of the operational amplifier is to increase the amplification of any input signal. So at the output, we are going to get an increased response of this input signal. So the problem with strain gauges is that it gives us very low resistances. Normally the resistance of the strain gauge are less than 1 ohm, and when we measure the resistance with the practical DMM or the industrial standard DMM, the ranges provided in that DMM starts from 100 ohm and goes to maximum for most of the devices is 2 mega ohm. Now the problem is that normal DMM is unable to measure the resistance, let's say, of 0.5 ohm, which is very less. So in order to increase the resistance such that our DMM can measure it, or at least we have in this range, we apply the amplification to it. So once we apply the op amp to it, we can get the, let's say, 0.5 ohm to come within this range such that our DMM can measure the resistance of the bending. So this is the practical example where an op amp is working side by side with any electrical device or electronic device such that it gets the value so that we can measure it in our measuring tools, in our example this being the digital multimeter or DMM. So hopefully now you understand the practical example of this op amp being utilized over here. Now let us come back to the operational amplifier and see what are the terminals and how we normally read an operational amplifier. So here this is an IC of the op amp. So normally it is the op amp IC. Let us take the example of LM741, or let us draw our own for better understanding. So let us say this is our IC. I am drawing the same front view or the top view shown over here, and we have certain pins 1, 2, 3, 4, 5, 6, 7 and 8. So we number it like 1, 2, 3, 4, 5, 6, 7, 8. Normally there is a notch over here and we something make over here which is called a groove. So notch basically gives us the ability to pick or attach the IC. So this is the notch that I was talking about, and mostly we have a small dot over here which is called as a groove. This basically tells us that where is the starting point of the pins. So now let us see, so this IC is LM741 mu A. So what is the meaning of these words? So normally LM stands for linear monolithic. This is a basically fabrication technique that the device is fabricated within a single layer. 741 is the series for op amps performing certain operations. So this is again decided by the vendor. Mu A stands from that this can take input as micro amplification. So the input of the signal will be in the micro values and it can amplify that signal. So this is what it means by these wordings on the op amp, and this is this information you can get from the available data sheet. Now let us understand what the pins are and what are the important pins needed for our course to do the analysis. So for our case, let us see, the first pin is called offset null. So and the fifth number is called offset null. So this is, we are going to see what does it mean. The eighth one is called NC. So it is shown over here, which means no connection. And the important pins that we need to study is the pin number 2. Sometimes it is referred to as non-inverting pin. Pin number 3 with a negative sign, this is called as an inverting pin, and this is basically where we put the input. So this is basically a non-inverting pin, and this is basically an inverting pin. The vendor can change the position of pin number 2 and 3, or the inverting and non-inverting. For example, in this case, this is an inverting negative sign and this is a positive sign, and this can be replaced, but 2 and 3 remains the input of the LM741, or the input pins of the IC. So 4 pin is the negative voltage supply, we say V negative. 6 is basically the output, we say V out, and 7 is basically the positive voltage supply. So these are the markings of the pins that we use normally for the operational amplifier. Now important pins for us will be pin number 2, pin number 3, which are the input, pin number 4, which is the voltage supply or negative voltage supply, pin number 6, which is the output, and finally pin number 7, which is the positive voltage supply. So for us in this course, doing the analysis of this amplifier, we are going to concentrate on these pins to do the terminal behavior, which means we are going to find the voltages and currents based on these pins. Now let us talk about the remaining 3 pins and what is the meaning of offset null, which is a pinning at pin 1 and pin 5, and what is this NC pin 8. So offset null is basically that kind of a pin which is used as an auxiliary pin. So what does it mean? So normally this pin is utilized when the life cycle of the IC gets degraded. So whenever the op amp is not performing at its optimum, we basically use this pin to apply an additional energy to the op amp, and this happens normally when its life cycle reaches. So normally an IC can last 15 to 25 years. So that is a huge time. That's why in most of the cases we don't utilize this offset pin, which is pin number 1 and pin number 5. So this is the meaning of the offset null. What is pin number 8? So pin number 8 is basically called NC, which means no connection. So internally it is not connected anywhere, and this is just there because it is due to the fabrication. Now why it is due to the fabrication? So normally in your data sheet you will also going to come across this term, that since this IC has 8 pins, so we normally write it as an 8 pin DIP. What is the meaning of DIP? DIP stands for dual inline package. So dual inline package means that how the ICs or the pins are fabricated with the IC. So if this is the jacket of the IC, dual inline means that we are going to fabricate 2 pins side by side in a single line. So in order to keep the coherency, this IC is made as a dual inline package. So we have 2 pins in a straight line. So this is what it means by dual inline packaging. So in order to keep coherency, this pin number 8 appears, but in reality this pin is not being utilized. It's just a dead pin to keep the coherency of the IC. So this is what it means, how to read the values of the IC. Okay, now once we know how to read the values from the datasheet of the physical IC, now let us look at its electrical symbol. So these are basically the electrical symbols that we are going to use in our circuit to represent an operational amplifier. So what is going to be represented? So this is represented by this triangular symbol. So this is the one input and this is the second input. Again, this is pin number 2 and 3. So we can say this is the input side represented by plus and negative. This can be swapped. Plus means it's a non-inverting, negative means it's inverting. So this is the positive voltage supply. This is pin number 7, so V plus. This is the negative voltage supply, pin number 4, V negative, and this is the output pin number 6. We call it as V out. So this is how electrically we represent the operational amplifier, or this is the symbol to appear or make it more clean. Normally this is how we utilize. So this is a triangular with the plus and minus voltage supply, and this is the pin or the input side of the IC, and this is the output. So what is this V plus and V minus? So this is basically called the biasing voltage. This is the voltage basically needed to wake up the IC or to provide the limitations of the amplification to the IC. What is this amplification limitation? We are going to look for this when we are talking about the regions operations. At this moment, just realize that V plus and V negative is basically the biasing voltage needed for the IC to operate. Why we need this? Because the internal circuitry or the design of the IC is such. Again, the internal circuitry we mean by this. So this is the internal circuitry. At this stage, we are not going to study this because this is not the part of the course, but you will have an understanding of this when you are studying the electronics basic course. At this point in time, we are going to assume that this is V plus V negative is the biasing voltage, and this is like a wake up call to the IC, and this is the maximum limitation or the bounding points for the IC. So what are the bounding points or the saturation points? We are going to look into this in our discussion for today. So now let us come to the further analysis of the IC or the op amp and the analysis in terms of the terminal behavior. So now let us talk about the terminal behavior of the IC. Since our objective is to, so let us see the terminal behavior of the IC or the op amp. By terminal behavior, we want to know what is the voltage and current associated with this IC. So let me draw the IC with its complete supplies and the current. So this is the symbol of the op amp. Here we have the input. From here we select the output. This is the positive supply and this is the negative supply. So let us put the values. So this is the positive V, this is the negative V, this is the output V naught, and this is the input. Let me call this positive and negative. So we know the input pins over here. So these are basically the input, positive and negative. Now in order to complete this circuit, let us draw the additional things. So here the V plus is connected to the positive terminal of the battery, V negative is connected to the negative terminal of the battery, and this is basically the negative, and we call this point as a common node. So common node is basically, you guessed it right, at a zero potential. And normally you might have seen that operational amplifiers pin doesn't have a ground. All the pins are having is the positive voltages and the negative voltages, input voltages and the output voltages. So in order to provide a negative to this op amp, we consider a common node. Common node is basically a point, for example, if you are using this IC to be integrated into a breadboard. So let us say if this is your breadboard with its vertical lines, and so normally if you take any IC, let us say this is my IC over here with its pins connected. Now in order to provide this as a common node, we basically take a common ground point in our breadboard. So this is as it, and we bring a wire from it and connect it to over here. So this is what it means by a common node. So you provide the common node as a ground to this IC when you are placing it on a breadboard. So this is your breadboard. Okay, so now let us see what is going to be the voltages and currents when interacting with this operational amplifier. So for the voltages, let us call this positive side as Vp, we call this the inverting side as Vn, we call the output as Vout, this is the VCC which is the negative, and this is the positive VCC. So this is the positive VCC and this is the negative VCC that is entering into the op amp. So again, since our ground is common, so we can say that this is a voltage rise for VCC or for the Vp, there is a voltage rise for Vn, this is the voltage rise for the output voltages, and the supply of plus VCC and negative VCC remains. So plus VCC and negative VCC, as I mentioned, is the biasing voltage, which means that if we have any signal, we are going to provide the positive cycle called the VCC to this point, and we are going to provide the negative cycle from the negative side of the battery to minus VCC. And again since it is an electronic device, the construction is such that we are providing the biasing voltages to it. So this is how the potentials are going to appear, and this is going to be our reference point. Again, Vp and Vn are the input side and V out is the output side. So whenever we are going to solve this op amp problem, we are going to denote the voltages as such. Now what about the currents? So all the currents generated by these voltages Vp, Vn, Vcc, minus Vcc and V naught are going to be entering into the op amp. So we are going to say that for all the currents generated by the voltages, the current is going to be inside the op amp. So the current generated by Vp is equal to Ip, the current generated by Vn is equal to Vin, the current generated by the output is going to be I naught, the current generated by V plus Cc is equal to Ic plus, the current generated by the negative voltage source is going to be Ic negative. So we are going to assume that all the currents generated are entering into this. Now why are we assuming this? Because an important point is that here we are considering this op amp to be an ideal case op amp. And why we are doing this? Because we want to study the terminal behavior and make our calculations of any given electric circuit as easy as possible. So for our understanding of this op amp's behavior in terms of the output voltage, we are going to assume that the voltages are Vp, Vn, V naught and the currents are all entering into the system. And this is what means by the terminal behavior for this op amp. Now once these things are cleared, let us look into the working of this op amp. By working of the op amp, we want to see that what is the region of operation. Region of operation for the op amp. In simple terms, we want to know that operational amplifier basically amplifies. So how much maximum it can amplify. So the output voltage, how much maximum amplification it can do, that is described by the regions of its working or the regions of operation. So for the operational amplifier, there are three regions of operation. The first is called the linear region. The second is called the saturation region with the positive, and the third is called saturation region with the negative value. So for all these regions, there are specific mathematical expressions associated with it. What are those expressions? We are first going to write them and then we are going to understand them. So the expressions for the linear region is that the voltage is going to be between plus and minus Vcc. The plus and minus Vcc are basically your biasing voltages, or now we say these are the limitations of your IC. For saturation region, the amplification is going to be greater than plus Vcc. For the third negative saturation region, the amplification is going to be less than minus Vcc. So what is this element that we are saying? So we are saying that this value of A, Vp minus Vn is basically the region where the amplification happens, or this is the output that we normally intend to get. So if we want to have a linear region, the amplification will depend on this mathematical expression where A is basically the gain of the system which is provided by the vendor, and its values are from 10 raised to power 4 and goes towards and ideally towards infinity. Vp minus Vn is the differential input of the amplifier. So again, this is the Vp minus Vn is this point, this and this. So this is the input that we are going to happen, and this is the mathematical expression for the gain. Now let us first plot this for better understanding. Let us say we want to plot this relationship. So this is the output of the amplifier and this is the differential input of the amplifier, because we have two input pins, and now we want to see the behavior and mathematically represent this. So normally this is Vcc by A and this is negative Vcc by A. So what we want to do is we want to keep the amplifier in a region between the biasing points. So this is my plus Vcc and this is my negative Vcc. So in amplifier, this kind of a graph is known as voltage transfer characteristics graph. So this is called a voltage transfer curve. It's not a curve, so we say it's a characteristics of it. Characteristics graph. So basically these kinds of graphs shows you the relationship between an input and output voltage, and this is what we are going to see. So in our case, we want our system to behave linearly, which means our circuit is going to be behaving something like this, and after that it is going to become saturated. So this is the point and this becomes saturated. So this is associated over here and this is associated. So this is the boundaries for the op amp. So basically this is the linear region where the amplification is happening. So this linear line is the point where we want to keep our operational amplifier working, and as you can see the relationship is linearly increasing. So for whatever input we have, we are getting a linear increase in terms of its output. So this is the linear behavior shown by this mathematical expression over here, and the output comes out to be this A Vp minus Vn negative over here. After that, if we go beyond this VCC boundary, it is going to be saturated, which means that it is only going to give you a constant value and not anything more than that. So this is the positive saturation. Similarly goes for the negative saturation of negative VDT if we are in this region. So this is the linear or the voltage transfer graph for this operational amplifier, and the main goal is to remain within this linear region or keep our amplifier operating in this region, and mathematical expression of this amplifier is over here. So this is how the amplifier basically operates in its region of operation. Now let us look further into this linear operation and see what else we can do in terms of analyzing this. So analyzing this, we come across very interesting phenomena, and that is that we had the equation of amplification of the operational amplifier, that the output voltage depends upon the gain A and the difference of input. Now let us see what else we can extract from this equation. So if we go to the market, the normal or maximum output voltage is around plus minus 20 volts, and the gain of is normally provided as 10 raised to power 4 by the vendors. So if we input these values into this equation, what do we get? So we get 20 volts as the output, gain comes out to be, let's say, 10 raised to power n, and then we have the input as a difference of Vp minus Vn. So Vp minus Vn comes out to be 20 divided by 4, which is 2 millivolts. Now you can see that the input voltage is just 2 millivolts compared to the output voltage of 20 volts. So it's a huge gap, and we can say that this 2 millivolts is negligible compared to the output voltage. It's a very small value, so we say that this is negligible. So we can say that Vp can be approximated to Vn, and this is a new thing that we have discovered when doing the analysis of an ideal operational amplifier. So we can say that since the input value is so small, which is 2 millivolts compared to the output voltage of 2 volts, we can say that Vp can be approximated to Vn. And this leads us to the discussion of two new things which we called as constraints in our analysis. The constraints are, number one, in terms of the voltage. So we can say that this Vp is approximated to Vn based on the scenario we discussed over here. So if the value of A becomes infinite, then Vp and Vn becomes equal to 0, or we can say that Vp becomes exactly equal to Vn. And this kind of situation in ideal op amp is called as a virtual short, and this is a very important term. So virtual short, what is the meaning of virtual short? Virtual short means that if I have my operational amplifier with inputs like this, so this is Vp and this is Vn and this is the output Vout. So what I can say is, since Vp equals to Vn, so there is an internal short circuit over here that both of these are connected, which means that whenever I'm doing the circuit analysis, if I know the value of one, I can immediately say what is going to be the value of the other voltage. So this virtual short element is very important, which we have assumed and utilized when doing the electrical analysis of an operational amplifier. and this is the first constraint that we self-impose on the ideal operational amplifier. So this is known as virtual short, where the Vp and Vn are internally connected, or there is a short circuit between these two elements. So this was the first constraint that we have. What is the second constraint that we are going to have? So the second constraint, so ideally when this virtual short happens, our circuit, as I mentioned, we want to keep our circuit operating in the linear region. We don't want it to go to the saturation region. So what we do is, normally when this condition appears, we also provide a negative feedback to the circuit, and this is known as, so if this is my negative and this is my positive, we say that the circuit is also operating in a negative feedback loop. So negative feedback loop is there to maintain the op amp working in the linear region. Again, if we don't provide this negative feedback loop means this path. So from the output, you are again inputting the value towards the input. So this is known as the negative feedback loop. If you don't do this, if there is no negative feedback loop, there is a chance that our operational amplifier may enter the positive or the negative saturation region, as we saw in the voltage transfer curve. So this is another thing that we want to keep when working with the ideal amplifier. What is the third thing? So the third constraint comes in view of the current values. We now have seen what happens to the voltages Vp, Vn, and the negative feedback ideally appears, or we want to create that. Now let's talk about the currents Ip and In, which is being generated from the inputs. So normally what we do is that for the operational amplifier, we keep the input resistance to be very high. When the input resistance becomes very high, we are going to say that the currents generated by Vp and Vn are going to be equal to 0, because the resistance is so high, the currents are unable to flow. But the output resistance Rout is kept at a minimum, let's say at 0 ohm, which means that the output current is not going to be 0, it is going to have a certain value. So does it make any sense? Yes, it can make sense. How? Let us say I have this op amp, and let's talk about in terms of, or let me draw it in a more fair way. So this is my op amp, and this is my Vp, this is my Vn, this is my output. So this is my Vp, this is my Vn, and this is my output. Let's talk in terms of the currents. So I know that the current entering or generated from Vp is going to be Ip, current generated from Vn is equal to In, and both are entering into the amplifier. Similarly, current entering generated from output voltage is going to be I0, and it is entering. Similarly, if I have V plus and V negative, so the currents coming from here is Ic negative, the current coming from here is Ic positive. Now, since we have concluded or made the hypothesis that the input current is equal to 0, so Ip or In equals to 0, but I0 is not equal to 0. So let us apply KCL, considering that all the currents are entering into this node, and that node is the op amp. So given this scenario, we can say that the amount of currents entering, so let us say I am taking that Ip plus In plus Ic positive plus Ic negative plus I0 is equal to 0. So all the currents entering I have taken as positive is entering equals to 0. Since Ip and In are equal to 0, so I get I0 is equal to minus Ic plus and minus Ic negative. So thus it still makes logical sense that although the input currents are 0, but according to the KCL rule, we are going to generate, or we are going to get a current at the output. So this is how the logical sense is making sense to us. So these are the constraints that we need to keep in mind whenever we are dealing with operational amplifier. Those constraints are in terms of voltages, which we call as the virtual short, and the other constraints are in terms of the currents, where the input currents are considered to be 0, but the output current is going to exist, and we have seen mathematically that the output current is really going to give us a certain value. Now let us look at the examples and further understand that how the operational amplifiers circuits can get solved easily. So let us take an example. So these circuits are very easy to get solved. So let us say I have this circuit. So this is an operational amplifier. So we have an inverting pin and the non-inverting pins. So from the inverting pin I am getting a resistor, and now I have the input as a DC voltage source and it is grounded. Let me call this as VA. From the non-inverting pin I have another source connected to independent voltage source. Let me call this VB, and this is the output, and from the non-inverting from the output we have a feedback, a negative feedback going into the inverting pin. So the value is 100 kilo ohm, 25 kilo ohm. What else do we have? We have the VCC of plus 10 volts and negative VCC of minus 10 volts, and we have the current moving in this direction from the I25 kilo ohm, and the current coming from the 100 ohm is in this direction. So let me write it as I100K, and we have been asked to find the output voltage V out, and the conditions we have been given is, so let us say for part A, find the output voltage when VA equals to 1 volt and VB equals to 0 volt, and the second part, what is the range of VB that we can find. So let us try to solve this and see how we can go about this. So this is the circuit that we have, and let us first populate this with the respective terminal voltages and currents. So let us, since this is negative, so let me call this branch as V of N. Let me call this branch as V of P, and we already have V of out over here. This is VCC negative and this is VCC positive. So normally we don't highlight this because the values are given, but just for your understanding we are doing this. We know that the current entering from Vn is I of N, and the current entering into the amplifier from Vp is I of P, and the current entering from V out is I naught, and so goes for the VCC plus and VCC negative. Now for the first part, we have been asked to find V out when the given voltage VA is 1 volts. Okay, okay, and here VA is 1.5 for the 5 for part B. This was missing, so I've added. Okay, so how you can find this? Okay, so we know that if we take this circuit and apply the node voltage method, the only essential node we see is over here. So when solving the amplifier, we always start from the input and we see that which points can be used as essential nodes. Here we see that at Vn we can have an essential node because it is connecting 25 ohm, 100 ohm, and then we have this power supply. So minimum 3 elements are connected. Other than that, we don't see any other essential node. So for Vn we can see that the currents are entering, so I can say minus 100 minus I25 plus In equals to 0. So I can say that In is equal to I25 plus I100. So this is the KCL at Vn. So applying the node voltage method at node Vn. So you know how to apply the node voltage method. So you have two ways to write this. The first way is you can directly say that the Vn minus Va divided by 25K plus Vn minus V naught divided by 100K equals to 0. Why we are doing this? Because we know for the node voltage method, we assume that once the essential node is made, we assume the currents are generated from. So from this node, one current will go in this direction, one will go in this direction, and the other will go in this direction. However, you can use this equation, but if you look at the original currents, they are in the opposite direction. So the original currents are I25, this is opposite to the direction we assume, and I100, which is opposite to the direction we assume. So we can take the original currents flow and write the equation. So the equation can be written in this form as well, that since the current is entering from the 25 resistor to our proposed one, so we can write the equation as VA minus VN divided by 25K. This is also acceptable. Plus then the 100 current is entering towards the node and it is originated from V0, so I can write as V0 minus Vn divided by 100K. So this equation is also fine, equals to 0. So both of these equations are fine. You can use any one. Let us use the second one for simplicity. So let us solve this. We know that the voltage is 1 volts, but we have to see what is Vp and Vn. So we know that by virtual short, so let us apply the constraint to find Vn for this equation. So for virtual short says that your Vp equals to Vn and your Ip equals to In, which is equal to 0. So these are the conditions that we are always going to utilize when working with amplifiers. So the virtual short condition says that Vp equal to Vn. So here Vp is directly connected to Vb and Vb is 0 volts. So which means that our Vp equals to Vb and it is equal to 0 volts. So it is going to be Vn. So which means that Vn over here is going to be at 0. So our equation then becomes Va, which is 1 volt, minus 0 divided by 25K plus V out, which we need to find, minus 0 divided by 100K equals to 0. Now it's simple mathematics. So you have 1 divided by 25 plus V naught equals to minus 1 by 100K. You multiply both the sides by 100K to get rid of this. So this cancels out. This becomes 4K plus V naught is equal to minus 1. So V naught is equal to minus 4 volts, and that is the answer. So we have found that the output voltage comes out to be negative 4 volts. And we can say the amplification has happened because the initial voltage was 1 volt and it has amplified into a negative 4 volt. So let us see whether it is falling within the range, whether it is in the linear range or it is in the saturation rate. So we know for linear region where the amplification use is basically needed, the condition is that we have to be in this range, that minus VCC should be less than A, Vp minus Vn should be less than plus VCC. Here minus VCC is the minus 10 volts provided to us in the question. So this plus VCC and minus 10 VCC are the saturation points of the amplifier. Saturation point means that this is the maximum voltage or the output the amplifier or op amp will give to us. So and our output is coming to be minus 4 volt and it is in the range of minus 10. So here our operational amplifier is basically working in the linear region. Now what happens if we take the value of Va equals to 4 volts? So if instead of taking Va equals to 1 volt, if we put the value of 4 volts, so our equation from here, if we write this equation, it will be 4 divided by 25K plus V0 divided by 100K equals to 0. So if we solve this, the value of output voltage comes out to be 16 volt. When 16 volt appears, this means that we have left the linear region because our result 16 volt is not following this rule, because our limitations are between minus 10 and plus 10 volt and 16 volt is greater than this volt. This means that if the value of Va equals to 4 volts, we have left the linear region and now we are in the saturation region, which is the positive saturation region, which means the maximum output of this amplifier is going to be not more than 10 volts, although we found the value to be 16, but the amplifier is not going to operate beyond 10 volts of the biasing voltage. Hence our real output voltage will remain at 10 volts. So this is what it means by the saturation region and the linear region. So now let us look into further examples and understand how the operational amplifier works. So we are going to look into two more examples. So the first one is, let us say we have this circuit, again a very simple circuit. So we have our operational amplifier, we have a positive or a non-inverting and negative inverting pin. Here the inverting or non-inverting is connected with a voltage supply of 12 volts, and then the output is connected to a resistor, then there is another resistor, and then it is grounded, and this is again connected to another resistor, and this is the circuit. The negative supply is connected over here, and this is basically a 12k ohm, this is a 2k ohm, this is a 10k ohm, and this is the unknown I naught that we need to figure out. So we are basically asked to figure out the unknown current I naught. Obviously we need to know what is the voltage drop across the 10 ohm to solve this. So in order to solve this interesting question, we are not given any biasing voltages. So again we are not interested in finding the negative VCC and positive VCC. So it is only given when we need to verify whether the operation is in the linear region or the saturation region. So in order to find this, assign the respective voltages. So this will be Vp, and this is going to be Vn, and this is the Vout that we have given. We know that the currents entering will be In and the current entering will be Ip. Again, virtual short says that Vp is equal to Vn and Ip equals to In, which is equal to 0. So this is the condition that we are always going to utilize when working with this. So let us figure out what is the voltage appearing at Vp, and that is going to be the same voltage. Since the voltage at Vp is 12 volts, so we know that Vp equals to 12 volts, and since Vp equals to Vn, so this is going to be Vn. So we have figured out what is the voltage at the input side. So now we know that the voltage appearing at this point is 12 volts, and this is at ground. So we know this is a voltage drop, that is be from 12 to 0 volts. So we can easily find the current over here. So the current across 2k is going to be V by R. We know that the voltage is 12 volts and the resistor is 2k. So the output comes out to be 6 milliamps. So this is the current that we have across the 2 ohm resistor. So we have basically found the value of current over 2 ohm resistor. Now let us do the further analysis. So we know that if this is our common point and KCL says that whatever current enters, it is the same current which is leaving. So if 6 amps is leaving from here, we know that 6 amp has entered from here as well. So the current over here is also 6 amps, and we can also verify that In, which is going over here and then it comes over here, is automatically 0. So which means the difference of both currents is going to be 0. So we can find the voltage across the 12 kilo ohm, which is going to be I into R. So we know that the current is 6 multiplied by 12, we get 72 volts. So the voltage appearing at this point is 72 volts. Now we know what is the voltage appearing at this point, so we can figure out the total voltage V out by simply taking the potential difference between here and ground. So the total voltage V out is going to be voltage at 72 plus voltage at 12 volts, and this is going to be 84 volts. So this is the output voltage, and you can see it has been amplified. The input voltage was 12, the output voltage is now amplified. So now we need to find the current. The unknown current I naught is equal to V naught divided by R. So this is 84 divided by 10, we get 8.4 milliamps, and this is the unknown current, and hence we have solved this easy question of operational amplifier. Now let us look at another example and see how to solve this. So in this example we have now two amplifiers. So this is one operational amplifier and this is the other operational amplifier. The values are plus minus and negative plus. At the output we have a resistor, then we have a common point, then we have another resistor, and then we have another resistor, and we are connected to it like this. Here we are again connected to a single resistor of 4K. This is 8K, this is 4K, this is again 8K. This is the unknown current that we need to figure out. From Vk we have a resistor, it is going into a voltage source, and then it is going again to another voltage source, and then it is grounded. So this is 5.8 volts, this is 2 volts. From here we have a positive value, and the negative value is again coming through a resistor to this point, and again this is coming from a resistor to this point. So we have a very interesting circuit with us. The values are 6K for this one, 6K for this one, 6K for this one, and 6K for this one. We have all the resistors, and again we need to find the unknown current I naught. Obviously we need to know what is the voltage drop over here at the output voltage, so we can easily find the I naught. So let us solve this. In order to solve this, we need to define the respective voltages Vp and Vn. So let me call this as Vp1. Obviously this is Vn1, this is Vn2, and this is Vp2. The currents entering are obviously going to be 0 because the currents are entering into the system. So this is the current In2, this is the current In1. Okay, so this is the current that is entering into the system, In1, and this is the current In2. Okay, so how can we go about this? It's a straightforward. We need to first apply the virtual short. What is Vp? It is going to be Vn, and the currents In and Ip is equal to 0. This is the condition that we need to follow. So let us start with first Vp2. Vp2 is directly having the voltage of 5.8 volts, and this is going to be Vn2. Again remember, here the 6K ohm is not going to give a voltage drop because we know that the input current Ip equals to 0. Since there is no current, there is going to be no voltage drop, and hence 5.8 volt appears directly at this point, which is Vp2, and we know the value of Vn2. So Vn2 is having a voltage of 5.8 volts. What about Vp1? So Vp1 is again going to have 2 volts appearing at this point. No voltage drop is going to affect this at 6 kilo ohm, but we have another voltage source in series. So this is going to be 5.8 plus 2 volts, which is going to be 7.8 volts. So Vp1 is equal to 7.8 volts, which is equal to Vn1. Again virtual short is giving us this liberty. So here Vn1 is 7.8 volts. Now I can find the current flowing over here. So the current will be I equals to 7.8 minus 5.8 divided by 4K, and it comes out to be 0.5 milliamps. So I know that the current flowing here between 4K is 0.5 milliamps. So again, according to the KCL principle, we know if the current is entering over here, so this is at 0 volt, the same current will go over here, and the same current is over here. So I can say that if I want to find the voltage at the 8 kilo ohm, it is going to be current multiplied by 8K, which is 0.5 into K, 4 volts. Voltage at 4K is going to be current multiplied by 4K, which is going to be 2 volts. So in total, if I want to find, so let us use this space, if I want to find the output voltage is going to be the sum of voltages in this vicinity. So it is going to be voltage at the 4K plus voltage at the AK plus voltage at the AK, 8K, which comes out to be 4 plus 2 plus 4. This is the same thing as we saw in the previous example. So this is going to be 10 volts is the output voltage. Again, the voltage got amplified because the initial voltage was 5.8 plus to 7.8, and the output voltage is amplified to 10 volts. Now the unknown current is simply 10 divided by 4k, which is 2.5 milliamps, and that is the output current that we require, and hence we have figured out what is the output current, which is 2.5 milliamps. And that is how you solve questions related to operational amplifier.